Alright, welcome to a new lecture. In the previous lecture we learned about the physical basics of railroad and steel wheel interaction, and we got an overview about the most important elements of railway infrastructure. Now we will take a deep dive into the central link between the rails and the ballast, the railway sleepers. As we have learned, the rail faces the stress of the railroad wheel. These stresses are transmitted from the rail to the structure it is mounted on. This stress can be split into three components: vertical stress, horizontal stress, and a torque at the bottom of the rail. The vertical stress is caused by the weight of the train and by dynamic forces such as braking or acceleration. The horizontal component is caused by guiding forces in curves or the hunting of the wheel sets. As the wheels do not run on the center of the rail but offset to the interior of the rail, the eccentricity of the force application point causes a torque at the bottom of the rail. To transfer these forces to the sleeper below the rails without moving them relatively from the sleepers, the rails are fixed on the sleepers with fastenings. Another stress that has to be considered is the contraction or expansion of the rails due to the temperature, which causes longitudinal stress on the ballast and the sleepers. Thus, railroad sleepers execute two basic functions. First, the load transfer. The sleepers distribute the stress from the relatively high surface pressure of the rail sleeper contact into a lower surface load in contact with the ballast. And second, the resistance to displacement. The sleeper or the support of the rail feet on the sleeper guarantee the track geometry and the gauge. After we now understand the basic functions of sleepers, let's have a look at the most important types that you will encounter in railway systems. Sleepers are distinguished by the material they are made from and by their overall design. As for latter, the distinction is commonly made between longitudinal and cross-sleeper tracks. In ballast bed, the cross-sleeper track is the most common on all railways, whereas longitudinal sleepers are infrequently used on slab track. Slab track is a type of track where the sleepers are resting in poured concrete instead of a ballast material, and this is giving them a particularly stable geometry and a long service life. Slab track will be an element of a following lecture where we'll look at this topic in deep. There are also many more variations of types, but this should give you at least an overview of the most relevant designs that you will encounter. As for materials, sleepers are commonly made from concrete, wood, steel, and artificial wood. The choice of material for the sleepers to be installed is made on the basis of technical, operational, and economic considerations. So let's focus on each one of them. Steel sleepers. Steel sleepers are subdivided into through sleepers and Y-shaped sleepers. Through sleepers were made from mild steel, but new through sleepers are not commonly manufactured anymore. Resupply is generated usually from refurbishment of old sleepers. Since the 1980s, there has been a new type of steel sleepers, the Y-shaped steel sleeper. It consists of two S-shaped bent, hot-rolled white flange main beams. As Y-shaped sleepers, disadvantages of the through sleepers are mitigated due to the continuous shape, which makes them highly resistant to displacement while reducing their footprint. For this reason, Y-shaped steel sleepers are being used in challenging situations such as steep climbs and very tight bends, while delivering a high stability and a high resistance to displacement.